Okay. Looks like we're all up and running finally. Well, good afternoon. Happy Monday, everybody. So just to give a little bit of a introduction to what's kind of going on this week and homeworks and stuff. I think I just checked a little bit ago the homeworks on Moodle, and it looked like a lot of people hadn't turned them in yet. So I think it makes sense to give everybody a little bit more time. So I think what's going to happen, I'll extend the deadline and bump the deadline back till Wednesday night for the homework, rather than like giving out a whole bunch of individual extensions. So I think we'll bump the homework back to Wednesday night so that you have a chance to go to the help session, talk to me if you need to tomorrow or Wednesday. We'll still be assigning a new homework today. And it's going to be a little bit weird because this one will be due not this week Friday, but next week Friday. It'll be due the 12th. So that's because this next homework assignment is a little bit on the longish side. And I wanted to get you, so I would recommend, if you're already done with this week's homework, take a look after today. You'll be able to at least get started on that next one. So take a look at that. That next homework assignment, then you have kind of 2 help sessions and quite a bit of time to look at that. It's going to be similar types of problems as on this one, with they're kind of like more advanced versions of the problems that were on this homework. So it'll give us some additional practice to do some more F equals MA stuff on control volumes, with a little bit of a twist. So that's what's happening. That will be due in, I guess it'll be like a week and a half. Just know we'll have another assignment that will be given out next week that will also be due that same Friday, but it's going to be like a short one. So there'll be one that's like a normal length assignment and one that's a short one. I'm kind of mixing up the dates a little bit like that so that we get back on. That's going to line up better with when we have the next exam, and it gives us time to get, like, I want to give you enough time to work on this next homework assignment, make sure you have help sessions to look at and think about. The other thing, and I guess this, you don't really need to think too much about this right now, but on Friday, we'll be having a quiz on some of the, like Reynolds transport theorem, F equals MA stuff. So I'll talk more about that on Wednesday, but that's coming up on Friday. Kind of on the stuff that we did on this last homework assignment. Yeah, so the dates are a little bit crazy. I'll keep Moodle updated so that you can check there and double check on the dates and stuff. But we'll push this homework assignment till Wednesday midnight. But I guess we're not like stopping the other stuff. So make sure you keep up with some of the other stuff in addition. Okay, so what we're going to be talking about today, we'll do another example today that hopefully will get us, again, a lot of the basic math isn't that hard, but I think getting your head wrapped around where you can look at some of these problems and figure out where the forces are and how they're acting and in what directions and stuff, it takes practice. So we'll do another example, but this will be, it'll be kind of an artificial example. You do some more fun ones in the homework, more like actual realistic examples, but we'll do this one because it's a kind of a dumb example, but it gets a lot of the different aspects in. So let's do an example. And again, this may help you as you continue to work on your homework. So let's say we have a system that looks like this. We have the ground, there's a little car, Okay, so there's this little car rolling along, and on top of this car, it has like a scoop on it on the front. So this is our and I'll kind of color that in. Okay, so it's got like a snowplow on the front. Again, this is kind of, I don't know where you would come across exactly this in real life. You wouldn't, but it has a lot of the kind of key features that are going to help us think through this. So our little car, this angle here is theta is 60 degrees. And what's happening to our little car is it's being shot with a jet of water. So there's a little nozzle here. Which is shooting a jet of water at our car that the velocity of that jet is 30 meters per second. And the area of our jet is 0.003 meters squared. Okay. And what we're going to be looking at is okay, so what's going to happen? So there's going to be, the jet is shooting against the car. It's going to kind of shoot off of that snowplow thing. And the car is going to be pushed, right? The car is going to be potentially, right? It's going to be pushed and accelerate. It's going to be moving. So we'll look at one snapshot where our car is moving and it's being pushed by this jet, and see what the forces are at that one snapshot. So at some instant in time, the car is moving this way with a velocity, we'll call this V bar RF, and I'll explain what that means. This equals, we'll call this capital U, which equals 10 meters per second. Okay, so VRF is constant. So we'll assume that it's moving at just a constant speed. It is the velocity of the reference frame. Okay. So like say this is the velocity of our reference frame, and this is where some of the actual tracking and stuff is a little bit challenging. But one of the kind of cool things, right, that we can look at is that this system here, where we now have things that are not stationary, right? We have a cart that's moving, we have water that's moving. How can we deal with moving things? The cool thing is physics doesn't really care, right? So the Earth is moving, but a lot of times we measure physics based as if the Earth is standing still. If you're in a car and you put your hand out the window, you're moving and the air is still, but physics doesn't care. The physics works just the same if you're moving and the air is still, or if you're still and the air is moving. So how we're going to look at this problem is we're going to pick a frame of reference and call that stationary. It doesn't matter if it's actually stationary, it just matters if it's not accelerating. So we have to pick a reference frame. So that's why I labeled the velocity of the cart VRF. So physics works the same with a stationary or an inertial reference frame. Right, and you understand what I mean by an inertial reference frame. This means not accelerating. So, okay, so where do we put our axes? So we can put axes on this problem here, right? If we say that this is X and this is Y, we could put axes on the Earth and use that as our reference frame, which is fine. Or we could say, well, that's kind of a silly place to put them because then we have this cart that's moving, right? It'd be like doing an experiment on Earth, and rather than using the stationary Earth as your reference frame, you're using like the stationary sun as your reference, and you'd be like, well, okay, what's our velocity? What's the Earth's velocity relative to the sun? And you get confusing. So why don't we pick a reference frame that's, and as long as it's inertial, it doesn't matter if it's actually moving or not. We just have to pick something that's not moving, call that our reference frame, and then measure things relative to that. So rather than this, let's put our axes, we'll put our axes right on top of the cart. And we'll call this Y bar and X. Let me erase that, X bar. So we'll pin our origin right at this front spot on our cart. I, again, apologize for that being a little tricky to see. But we'll pin our reference frame, our axes, right at that start. And we can write, instead of, so now our momentum equation becomes the same but a little bit different. So we have now the forces equals d dt, same with our control volume, but now this is v, and we'll call it x, y, z, x bar, y bar, z bar, rho dv, plus the integral for a control surface of x bar, y bar, z bar, rho dot dA. Okay. So this applies to any inertial control volume, right? So that would be the velocity of the reference frame is constant. And V, X bar, Y bar, Z bar is the velocity with respect to the reference frame. Okay, so so what we have to do if we look at our cart, we have to picture our cart. You're standing on the cart, and you are saying, right, you're right here, and you're looking, okay, what is the velocity of this jet of fluid coming toward me? What is the velocity that it's leaving away from me? You're watching, you're standing there, you're the observer, you're on the cart, and you're looking at velocities relative to you. So that's what we're doing in these problems. You pick a reference frame, you're standing there, and you're looking at what's the velocity with respect to me. And that's what, so the notation here on this problem, this just like the velocities here, v, x bar, y bar, z bar, it's the same velocity that we've always been using. It's just to make a little bit extra clear that this is with respect to a potentially moving reference frame. We've always been doing, all of the problems that we've solved have been on a moving reference frame. It's just been like the Earth that was moving. And we're used to doing velocities with that. But if we have our reference, our cart or something like that moving, it can get a little bit trickier to keep all of the different velocities separate. So let's do this cart example. And I think that will help us figure out exactly how some of this stuff works. So this is kind of a, like I said, this is an artificial example, but it combines a lot of different stuff. We have now a moving reference frame. We're going to have an X component and a Y component because there's a directionality stuff in there. So I think it works well as an example for those reasons. Okay, so our governing equations, our governing equation is this one that I have boxed here. So let's solve the cart problem. So the first thing we're going to look at is steady flow. Okay, right, this makes this part equal to 0. This is x, y, z, x bar, y bar, z bar. So that part equals 0 if we're steady flow. We're going to look at uniform incompressible flow, right, which turns our integral into a sum. Okay, so our real equation that we have to care about is the sum of all the forces equals the integral over our control surface of v xyz rho v dot a. Okay, so this is in 3 dimensions. So this is in vector notation, but we can split this up into fx equals the sum over our control surfaces of u. So let me again denote this as with respect to our reference frame. So u, x, y, z, rho dot a, and fy is the same thing. So we're going to split it up into the 2 separate components, x and y. let's look first at the X component. So we'll look at the component of the force that's pushing the cart in the X direction. So we would have plus Rx plus F Bx, right? All of the different types of forces which we might have equals our control surfaces of dot A. Okay. And then we have to look again at what our control surfaces actually are. Like, what are we summing over? If we go up and look at our ramp, right, we're going to have our jet of water is going to be coming out of there, flowing up this way and shooting off in that direction. Right, so let's look at our control volume. I'll draw it again down here. Our CV is going to be something like this. Now, look at, going to be something like that, where this angle here is, well, let me draw it. This angle is 60 degrees. So there's going to be water coming in there and water leaving out there at a 60-degree angle. We'll call this control surface 1. And where it's shooting off of the ramp is control surface 2. Right, so this part, this is the only solid part. This is the snowplow part. Does this kind of picture make sense at least? So our areas are A1 is 0.003 meters squared in like the negative X direction. A2 is 0.003 meters squared at 60-degree angle. Okay, so A2 is pointing out, again, it's an outward normal. So it's pointing in the X and Y direction. It's pointing at that 60-degree angle. But they're both the same area. Because the jet, by conservation of mass, if the jet's not changing velocity, the area is not changing. So it doesn't matter that it's kind of smearing out and going off this ramp. As long as it's not changing velocity, the area functionally is staying the same. We're assuming a uniform velocity profile. So they're both equal to the jet diameter. They're both going to be outward normals at those points. We have to keep track now of velocities relative to that place, that control volume, right? So our entire control volume is moving to the right at 10 meters per second. So we have to look at what is the jet velocity relative to that. So how do we measure velocity relative to our moving control volume? Okay, so at side 1, U1 is the velocity of the, well, let's write, so V1 XYZ, or VXYZ1. I don't know how you want to denote that. But the velocity is, the magnitude of it is going to be the velocity of the jet minus capital U minus the velocity of the cart. I'm using U, right? If we go back up, so how fast is the jet coming toward you? Well, the jet's coming at 30 meters per second, but you're going at 10. So it looks like it's only coming at you at 20. So that equals 30 meters per second minus 10 meters per second, 20 meters per second. That's the speed, and that's coming exactly in the x direction. So it would be 20, the vector would be 20 meters per second I hat. At the side 2, again, the magnitude of the velocity is going to actually be the same thing, because it's coming in at you at, and it's coming in towards you at 20 meters per second. It's not slowing down, so it's going to be leaving the cart. The magnitude is still the same, so it's going to be still V jet minus U cart, 20 meters per second, but it's now at a 60-degree angle, right? Because it's shooting off the cart at that 60-degree angle. So how do we deal with the x momentum? So that's going to be the velocity vector. We need to find, so the x velocity, which is u1 and u2, because those are two things that we care about. So u1, little u1, is going to be equal to the x component of v1, which is just 20 meters per second, u2 is the x component of v2, which is 20 meters per second, but it's at an angle, so times the cosine of theta, which is cosine 60, which is 0.5, so that's 10 meters per second. So it's only 10 meters per second in the x direction. It's the speed is still 20, but it's 10 meters per second in the x. So our forces in the x direction plus Rx is equal to, we're going to go back to this sum. So we have to find, so it's going to be U2 rho. Now it's the velocity dotted with the area. So the velocity is, looks like I killed it. The velocity is 20 meters per second here. That's the speed that's coming in. The area is this, and it's pointing in the negative x direction. So they're pointing in both in the I direction in opposite ways. So the area is pointing in negative x, the velocity is pointing in positive x. So the dot product is just those two things multiplied. But it's a negative, so it's negative, this should be, sorry, U1, A1. Okay, plus, now the speed in the x direction, U2, times the density. Now we're going to do the dot product of the velocity and the area at side 2. And so we're looking at this side here. So that would be like A2, and that is V2. So the velocity and the area are now both at a 60-degree angle. So that's why we keep the, when we write this, where's my equation? When we write this equation, this one stays as U, that's the x component. This one stays as V vector. So when we've done things in a single dimension, it's like all in the x, then it kind of is easy to just be like, oh, it's U squared. But they do matter because it's, if you have something that not everything is in, say, one direction, then they might actually be different, like the total speed and the x component of the speed. So this becomes U2 times, now this is like the magnitude of V2 times A2, right? Which is the same thing that we did before, but those happens to just work out to be U1. Okay, so the net force, this equals Sx plus F plus Rx. So this is, is this U1 squared rho A1 plus U2 rho so this would be really the same, so we'll call this V2. I'm just rewriting the same thing. I don't know why I did that. So let's start to plug in some actual numbers. So that's 20 meters per second times the density, which if this is water is 1,000, times the area, which was 0.003 square meters, plus now this is 20 cosine theta meters per second times 1,000 times 20 meters per second times 0.003. And these two should go there, but I ran out of space. So this is, that's all multiplied. So yeah, Liz. Because they are both at a 60-degree angle. So it's a dot product between those two vectors. So because they are both pointing in the same direction, the dot product is just the multiplication of the magnitude of both of those things. So, yeah, you're right. This is a negative sign here, negative sign there. Yeah, you're right. Thank you. Yes, squared. Yeah, so that 20 should be squared. Okay, so you can see there are a lot of easy places to mess up the algebra. But the tricky thing is the differentiating between the x component of the speed and like the overall speed when you have stuff happening with angles. Maybe another way to think about this, right? What we're trying to find is the force pushing in the x direction on the control volume. We know it's going to, that takes this jet that's initially going all in the x direction and bends it up to an angle. So right, if you think about it just in the x direction, it's going from 20 meters per second in the x direction, and it's slowing down to 10 meters per second in the x direction. So that's what's happening in x. It's going from 20, it's bending up to a 60-degree angle, but like just along x, it's going from 20 and slowing down to 10. So that's going to be where the x force comes in. And then the y force is going to be, okay, what has to push up on that to keep it started initially at 0, because it has 0 y component. We have to push up on it to get it to be moving at sine 60 times 20 in the y direction. So we kind of have, our x force is going to be slowing down the jet. Our y force is going to be pushing to speed it up into the y direction. So those are going to be the two components that we end up having. Okay, so this is negative 600 newtons. Right, this is force. This is the force on the CV. So it's slowing it from 20 meters per second down to 10 meters per second in the x direction. Right. The flip side is the jet is exerting an equal and opposite force on the cart. So the jet is pushing the cart with a force of 600 newtons in the positive x. So okay, this is the sum of all of the forces acting in the x direction. But we can actually simplify this a little bit because this P so the atmospheric pressure is everywhere. So there isn't a force on our control volume from pressure. It's atmospheric pressure everywhere. So this is gravity is in y. So both of those terms will drop out. So the only force on our control volume is the reaction force, which is the force of the sloped snowplow thingy on the front pushing against the water. Okay, we can do the same kind of thing with the y direction. So in the y direction, our y momentum is basically the same thing. Now we're summing over our control surfaces of not little u, but little v. This is where notation and penmanship come in handy. So little v rho capital V yz dot A. So our, for the same reason, so pressure is atmospheric everywhere. Gravity is in the y direction, so F equals m equals minus mg, where m is the mass of the water in our CV. So the total mass of water that is currently in contact with the front of the cart, that water is going to add a force based on its weight. So it's going to be, it's sitting on the cart, it's going to add a force based on that. And then Ry is again the force that is kind of the snowplow thing that is pushing up on the water to get it to bend and eventually going up at an angle. So if we look at what this would be, so this is m or minus mg plus Ry equals, so this would be V1 rho V1 XYZ dot A1 plus V2 rho V2 XYZ dot A2. We can simplify this because here V1 is equal to 0, right? There is no y component. At side 1. So this whole term crosses off and equals 0. So we're just left with minus mg V2 rho dot A2. So our forces, the force, the reaction force is equal to, so the y component, V2, so that's 20 times sine 60 degrees times the density, 1,000. Now times this dot product. Right, in the dot product, they're again both pointing in the they're both pointing in the same angle at 60 degrees, and they're both, the velocity vector and the area vector are both at that angle. So that's just a simple multiplication. So this turns into 20 meters per second times 0.003 meters squared. Minus mg plus. So the reaction force is equal to the sum of that whole thing, so 1,039 newtons plus mg. And right, what was Rx was 600. Is that right? Minus 600, minus 600. So the jet exerts a force of 600 newtons to the right and 1,039 newtons plus the weight of the jet. So plus a little bit down. We could figure out the weight of the jet only if we knew like the exact dimensions of that scoop part. If we knew that like the scoop was 3 meters long, we could say, okay, the jet is 0.003 meters squared times 3 meters long. So you could figure out the volume and the density and figure out the total mass of water. It's going to be in a problem like this, it's going to be relatively a small effect. But right, you can think of it, the cart has to push the jet from going sideways. It has to turn it and push it up. So there has to be a force pushing up on that jet to get it to turn up. And there also has to be a force pushing against the jet to get it to slow down in the X direction. So those are the two components of the force. And just the thing to remember as you're going through these, this first term here, this first term here is the X component of the velocity. But this second grouping, then you're looking at the velocity and the area together. So that usually is like, what is the velocity dotted with that area? They're usually pointing in the same direction because that's the easiest way to do it. So that's usually like the speed times the area, not the X component of the velocity. It's usually like, what's the total speed as you're dealing with things, especially if you're dealing with things at weird angles. But like I said, so we'll do another fun example. We'll say, okay, what happens if the cart is actually accelerating? We'll do that next time, which will be kind of fun. At least we'll do it a little bit next time. I don't think we'll go all the way through it, but it'll be interesting at least to see how that modifies things. But that's all for today. So get the homework in by Wednesday, and we'll see you all then. You can just turn it in.